Thank you very much, and I'm very grateful for the invitation of the Institute and the Academy to give here this seminar. And the matter, I first studied as a physicist and then turned economist. I found it back as an economist, so you might see the two trains which come together here. Indeed, at the 50th anniversary of the first Solvay conference in Brussels, I was a student in physics in the last year. And all the students, maybe 15, were assigned to one of the guests at the conference. And I got Werner Heisenberg. I was his boy in a certain sense for 3 days. I had to show him Brussels. He knew. To go to a restaurant, was not interested. He was interested only in discussing physics, especially his physics. And for me, it was, of course, absolutely fascinating to discover how he was led by the logic of the theory he had been in 1926 building quantum theory. He was led to his own surprise to the uncertainty principle. His own surprise, which very well shows that you cannot plan for great discoveries in science. But neither he nor me, we were aware of a book written published in 1921 by John Maynard Keynes. We were both physicists, the student and the genius. So we didn't know that book. And I, of course, discovered that book later on when I came to economics. And in that book, Keynes, it is a treatise on probability. It's not his major work, but it's very interesting. And he makes in that book a very clear distinction between risk, which is uncertainty completely structured by objective probability distributions, and genuine uncertainty, much more difficult to deal with. So we didn't know at the time, Heisenberg and myself, that what he was dealing with was risk, which is odd, of course. You don't speak of risk with elementary particles. But it was risk because everything in quantum mechanics is structured by probability distributions that the theory predicts and then you check statistically, for example, in Geneva. And when you go to not these solitary elementary particles, which you never know where it is and how fast it goes. But when we go to large populations of particles, it's completely deterministic in a statistical sense. There is no uncertainty there, paradoxically. And when we use our computer, when we go to hospital for a check, or when we use a laser in its various disguises, we are not aware of Heisenberg principle. Everything seems to be completely predictable and deterministic. So it's no surprise in this case that Heisenberg principle was never a matter of public controversy, even if it has been a matter of scientific controversy between the happy few. With other sciences, ecology, medicine, oceanography, climatology, the situation is radically different. You enter the world of genuine uncertainty. And then you have, I wouldn't say that quantum mechanics is easy, but in a certain sense, it's straightforward compared with these different sciences, where uncertainty is at the core of a matter. And then you leave the world of theories and you enter the world of models, which is very well explained by Henry Pollack, who is a geophysicist at Ann Arbor. And he explains why complexity leads to uncertainty, to genuine uncertainty. Now, we should not panic for two main reasons. And we should be very much disturbed for the third reason. We should not panic because not everything is uncertain, even in climatology, in oceanography, and so on. By the way, you have cores in these sciences of certain knowledge. And exaggerating uncertainty in these cases is a trick, but a political trick or an economic trick, not a scientific way of dealing with things. Take the example of a forest. Clearly, there are disagreements, there are models competing, but they have important elements in common in their results. They have, for example, in general, agreement on what are the main interactions in the ecosystem, which drives in a certain way the dynamics of the ecosystem. Take climatology. Again, it has been a trick, and I will come back to that, to say that everything is uncertain, so you cannot rely on that science. Probably, if you speak with climatologists everywhere in the world, you will get the feeling that maybe on 70% they do agree. Well, they do agree, the models they use do agree. And these 70% give you results, certain results, results you can accept as certain, in such a way that on these results you can build a policy. You have not to wait for the sound science that President Bush wanted. It seems certain, if you listen to these climatologists, it seems certain that the increase in the mean temperature of the Earth will be more than 2 degrees. Certain. How much more uncertain? 3, 4, 5, as considered by Nick Stern in a recent paper in the Financial Times? That's uncertain. But clearly, you already have, with what is certain in that science, you clearly have a core of knowledge on which to base some policies, not some science. Still, there remain a lot of uncertainty in climatology, in medicine, in ecology. And it's not enough to reassure yourself that a core is certain. It's nice to have also methods to rationally deal with what is still uncertain. And when I say still, we should be cautious about that. It can be understood as we are on the path at an intermediate station, I would say, to a certain knowledge. But we should not wait for certainty to take some decisions. We have to take decisions in the uncertain, at the uncertain stage where we are. But it can be more fundamental. It can be that we will never reach a certain, completely certain knowledge in a certain domain, in some domain. And there it is even more, let's say, stupid to ask, to wait for certainty. It's like Godot, never come. We have methods to deal with genuine uncertainty. And I will devote maybe 10 or 15 minutes to discuss these methods. I will especially point to 3 of them. The first one is the concept which I will illustrate of reliable, uncertain science. Seems to be paradoxical. But reliable for decision science, even if it is uncertain to a certain extent. Then I will discuss the generalization of the von Neumann-Morgenstern method to deal with risk. Risk is a special case of uncertainty, and in that respect, Werner Heisenberg was right. And von Neumann and Morgenstern, in their famous book on game, well, establishing game theory in the 30s, published in the 40s, they proposed a model of a rational decision maker under risk. And that model was, in a certain sense, in Kuhn's sense, a scientific revolution in economics and in decision theory. And it, as children, I would say, most of the models that, for best or worst, are used in finance, in insurance, and in other fields of management and economics. For example, the models establishing the prices of derivatives are just an offshoot of von Neumann-Morgenstern basic model. About 15 years ago, mathematicians and economists, especially Italian ones, French ones, and some Americans, developed an approach to the decision under uncertainty, which is a generalization of the von Neumann-Morgenstern model. And I will discuss it for 5 minutes. And the third approach, a rational approach to deal with genuine uncertainty that I will discuss, is even more recent. It is the search of advanced signals which warn you about the proximity of tipping points, of what the mathematicians call bifurcations, because at such point you go to another trajectory and you are no longer able to come back to the previous trajectory. For example, suppose if we burn so much fossil fuels and we emit so much CO2 that we would have a massive release of methane. That would be a tipping point, and we go to a completely different trajectory in our climate. That approach of signaling tipping points has been developed by ecologists and mathematicians. And the first kind of tipping point which has been studied is, for example, a tipping point in the quality of the water in a lake. And they have identified precursors of that, so that you can signal in advance that you are entering a dangerous zone and that you should do something about that, or accept what is happening. All that is based on rational models. And it represents quite a bit of progress during the last 15 years. There are other rational approaches to uncertainty. And that approach is to make the most of uncertainty, fabricate it, increase it to reach some goals. For example, blocking policies which are not according to your interests. In a certain sense, it's a science as well. Frank Luntz is a genius of communication, of manipulation of opinion. He was the main Republican pastor in 2004, and he advised the candidates, the Republican candidates, from representatives to the president himself, how to use some words, avoid other words, use some perspectives, avoid other perspectives. He's still very active. He seems to come back as the first advisor in these matters of the Republican candidates, and especially of Gingrich, with whom he had worked before 2004, when the Republican Party took the House of Representatives. You need to continue to make the lack of scientific certainty as primary issue in the debate. That's central. And I will devote a few minutes to illustrate the strategies and the tactics, which are quite rational. We are not at all speaking of an irrational approach to risk and uncertainty. It's a different rationality pursuing different objectives. Some of you may have heard of the theory of asymmetric information in economics, for which Akerlof, Spence, and Stiglitz got the Nobel Prize. The essence, and by which Stiglitz has recently been able to show that one of the deep reasons of what happened in the crisis in the United States is a reverse asymmetric information between, for example, buyers and sellers of subprime titles. The essence of that is captured by For Economists, a famous paper, which is on lemons and peaches. That paper Akerlof wrote when the three of them were starting to work on that new approach to economics. And he wrote a very nice, very amusing paper, which was turned down by the first-class journals to which he presented it. Eventually, he was able to publish. And so it is about lemons and peaches. And lemons are, in Californian parlance, are bad used cars. Peaches are good used cars. Suppose you want to buy a used car. You know that you prefer a good one, but you know which is which. It may happen that the sellers of good cars or good used cars spend money, make efforts to signal, and it's the reason why signaling and asymmetric information are connected, to signal the quality of what they sell. But it may happen that that's just too expensive, and that they accept a market, a uniform market, where the buyers cannot distinguish good and bad used cars. And you have one price kind of average. Or it may happen that the market just disappears. But suppose it doesn't. In certain circumstances, it doesn't. It doesn't. And what happened on that market is that you don't make money being good. You make money faking being good. Exactly what happens in that large market of selling false signs and fabricated uncertainty. Which side is false? Which side is true? We know. Most people don't know. Most politicians don't know or don't want to know. And many institutions have a vested interest in making the situation as confused as possible. So that's the spirit of my contrast between scientific uncertainty and fabricated uncertainty. Let's go back to scientific uncertainty. And let's go back to that concept of reliable uncertain science. At the end of the 1980s, the British government was in a difficult position because a mysterious disease had started, first in Wales and then in England, never in Scotland, to a very serious disease for cows. It was called mad cow disease, And what was that disease? What to do about that? Should you ban British beef? Not an easy decision for a government. The scientific advisors of the British government at the time developed a pseudo theory of a barrier of species. Whatever the cause of illness in the cows, it will not infect humans. It was something specific to cows. That was destroyed, as you know, the theory is destroyed as soon as you have a counterexample. That was destroyed when two biochemists at Bristol University inoculated the disease to a cat. And also, a kind of disease of the same family, it seemed, was developing in young people. The new variant of the Creutzfeldt-Jakob disease, destroying the brains. The British government was without any scientific basis to decide about what it should do. But a scientific, uncertain scientific basis which proved reliable was being developed at University of California, Los Angeles, in the lab of Dr. Prusiner. Dr. Prusiner was working on mice and was studying illnesses of the brain in the mice which seemed to be caused by prions. And a lot of skepticism was about that, because never before such an element of the mice body had turned into a pathogen to the brain. Prions are very important for us. Recently, at the School of Medicine of Columbia, it has been shown that they are the support of our long-term memory. But when Prusiner showed they have some mutations, they can become extremely dangerous when they migrate to the brain. And they induce fatal brain diseases. Prusiner had good, in the sense of applying rigorously the scientific method, had good empirical data on the mice, not on humans. He was able, going to theory, as Poincaré said, you need bricks to build a house, but a house is not just a heap of bricks. So he needed to explain what was happening. And he had been able at that time to identify some, I would say, events at the molecular biology level which explained these transformation of prions into pathogen agents and then their action on the cells of the brain. He was not able to explain all the stages. He had some knowledge, some explanation of the path, but some pieces of the path remained difficult to understand. Clearly, that was uncertain science, which uncertain science obtained by standard scientific methods, and it seemed on its way to a complete explanation of a mysterious illness, and of course very important in the consequences it could have in medicine. So that was, I would say, clearly still uncertain, to a certain extent, still significant extent, but due to the way it had been obtained and due to the body of knowledge already available, it could be called reliable, uncertain science. And it was on that science that the British government, when they went aware of these results or these developments, the British government decided, and the European authorities as well, decided to ban the English and Welsh beef. A few years later, Prusiner completed his results, his explanation. He got a complete, certain science of these phenomena. But it would have been a tragedy to wait for that certain science. It would have been a tragedy, and we have an example of such tragedy, asbestos. Almost everything was known in the 50s, and still they waited, they delayed. In the 50s, the science of the cancers which were induced by asbestos was almost certain. Yes, at least reliable, uncertain science. And on that basis, the decisions which have been taken 50 years later should have been taken at that time. Rationally. So that's for the concept of rational, reliable, uncertain science, which certain people say it's exactly the status of climatology now. Other people contest that. And of course it has some consequences on policies. I will come back to that. But I want now to illustrate the second approach, a rational approach to dealing with uncertainty. When you are in a science where it's not completely certain and possibly it will never become completely certain. And just a bit of history. So you have von Neumann Stern with risk, uncertainty completely structured with objective probabilities. You have two people Maurice Allais, the French economist who also got the Nobel Prize, and Ellsberg, David Ellsberg, the man who is most known for the Pentagon Papers, which he leaked at the end of the Vietnam War. But he also constructed a paradox. Both Allais and Ellsberg constructed paradoxes, and paradoxes were discrepancies between the results of the von Neumann-Morgenstern model and attitudes, decisions that people routinely take. So these paradoxes pointed to the necessity of reconciling the model with empirical data, which the model wasn't comfortable with. And that took 15, 20 years. And we now have a general model of decision-making under uncertainty, under genuine uncertainty. And you can have a flavor of what it is if you go back to the Stern Review. Yes, the Stern Review on the economics of climate. There is a chapter there on risk and uncertainty, and Nick writes this. So, you are facing uncertainty. You are a rational decision maker. You are not constrained by the axioms of von Neumann-Morgenstern, which made these models fit only for risk situations. A bunch of mathematicians and economists proved that under very mild assumptions, much milder than the assumptions made by von Neumann and Morgenstern, you can represent the decision-making in the following way. The decision maker decides as if is important. We are not all the time deciding by making calculus in our brains, of course. Decides as if he would consider reality through the lens of a family of probability distribution on which there are genuine uncertainty. It's like what once Arrow and Ulrich presented as you flip a coin to decide how you will flip the next coin. And of course you have probabilities of doing the next uncertain event. So you have you act as if you had a family of probabilities, and as if you had in your mind a utility function on the events, possible events, just like in von Neumann-Morgenstern, and you decide as if you would, on that basis, maximize a sum, a weighted sum of what Nick Stern calls a pessimistic view of a world, a probability which gives you a catastrophic result, and an optimistic view of a world, a probability that would give you a very nice result. In mathematical terms, it's this, where the first term is the pessimistic view, and the weight of that term is your aversion to uncertainty, which is a generalization of the aversion to risk that you have in the insurance and in the finance models. Let's just mention one or two applications of that. When the reinsurance companies, these companies which insure the insurance companies, for example, Swiss Re or Munchen Re, when these reinsurance companies have to make a decision on events for which they have no reliable statistical information, well, then they are in the uncertain world, and they use that kind of formula to decide whether or not to take it in their portfolio, whether or not to take a part of it, and which part of it in their portfolio. And in the United States, you have special agencies which evaluate the portfolio of all the insurance and reinsurance companies on the market. Just like Standard & Poor's for financial matters, for example. And what they do is that they don't any longer evaluate these portfolios of the various companies. They don't evaluate them on the basis of a mean value, because if you use a mean value, you lose a lot of information, maybe uncertain, but still valuable. They evaluate the portfolio with that kind of approach, especially with using a family of probabilities, distribution of probabilities, and not just one distribution, considered as a mean distribution, which has not much sense. I mentioned the third approach which I wanted to present, which is the signals going to tipping point. I think I cannot devote much time to that now, but it's in the paper which I gave you, which I sent you this morning, and which can be put on the website. And also, there are 2 or 3 papers in Nature, which are mentioned in my paper, which give a very interesting view of the applications on ecosystems and climate. Tipping points in ecosystems and tipping points in climate. But I want to finish by giving you an idea of the world of manipulation of uncertainty. It started a long time ago. It started with tobacco. It started when, in the 70s, institutions like the Institute of Health, public institutes, research institute in the United States, and some other, the Catholic Institute in New York also, they started to produce models showing the effects of smoking on health, with solid empirical, of course, data to substantiate these models. And Benson and Hedges, American Tobacco, and all these firms, they immediately saw the threat. And so they decided to counter that threat. How? With counter science. They didn't want to come, I describe that because it's a model which has been repeated time and time again, and now which is used to fight climate science. So they didn't want to come on the forefront, because they had a bad reputation anyway, and they were not credible. So they created in-between institutions with a look of serious science, the lemons, and with nice names. For example, the first one which was created had a name which is greatly respected in the United States, more than in France. And that is, the name was the Alexis de Tocqueville Society. That was the first lemon created to respond to the serious science which was produced by the official institutes. And they attracted scientists. And these scientists, what was important was that they had a name. It's a signal, just like in the model of lemons and peaches. They had a name. For example, they attracted a man who had been one of the prominent solid-state physicists in the United States, and then for 7 years, president of the National Academy of Sciences. that obviously for everybody is a great scientist. He had no knowledge of medicine. Well, a bit of knowledge, because he has also been, he was really, like in the Soviet Union, a marshal with all these decorations. He had also been the director of a Rockefeller institution in New York. So he got some sense of medicine. And he was the prominent scientist of that institution. So an institution will looked serious with a man who had a great reputation. He of course hired a bunch of lesser scientists, but still with always that characteristic that these scientists had done something interesting in science, but never in the science which was relevant for tobacco. And with that, and of course with the help of lawyers, you know the importance of lawyers in the United States, they delayed by 30 years the final condemnation and the final ban that was pronounced by American courts. 30 years. And that tactics was used in many respects. Pollutions, ozone layer, even the, you know, the Star War, that is the program of President Reagan to develop rockets, anti-rockets, where prominent scientists were fighting prominent scientists like Carl Sagan, who was of course against that. And, well, confusion was always, of course, on the side of the people who contested serious science. But that, and I finished on that, that took its maximum development with climate. You have not, with climate, you have not just Benson and Hedges, American Tobacco, and 5 or 6 tobacco farms. You have Exxon, you have Peabody. Peabody is the largest producer of coal in the United States. You have Shell, you have BP, you have General Motors, you have the Koch brothers, of course, with their empire of firms. And they have created not just one fake scientific institute, but a dozen, with nice names. The Society for Sound Science, the Marshall, a very respected name also in the United States, the Marshall Society, and so on and so on. I give a few examples, some being in a certain sense laughable, but it's serious. And you still find some of those who worked for the farms on tobacco, you still find them on climate. And some who were recruited by Reagan, well, in a certain sense, they found another job with climate. One of them famously said, anyway, the ecologists, they are like watermelons. Green outside, red inside. So it's the same enemy as the communists. And you have some of them, they go, of course, to the talk shows, they write, they give conferences, they are nicely paid, which I think is not, knowing a couple of them, is not the main motivation. The main motivation is they have their scientific future behind them, and they still want to be somebody. And I see the same in France, with a few of my colleagues. And it works. It works for many reasons, but one is fundamental, and it has been captured in this. these scientists which work for these interests are not at all constrained by behaviors, attitudes, rules that constrain us as scientists. And most of the scientists, the serious scientists, they don't like to have debates like that. You know, you have debates in the United States where you are a television, you have a lemon and a peach, and they are considered as equal. Equal because they have two opinions. They don't share the opinions, which is what interests, of course, the television. And they don't share their opinions, they fight. People are interested, people are glad of that, and that's it. Science in all, well, they succeeded in having science considered by the opinion and the politicians, by the lay people and the politicians, as just another opinion. And the result is that in 2007, the poll by the Pew Center showed that roughly 65% of the Americans thought that climate change is the result of human actions. In 2010, that percentage went down to 40. It works. I will not conclude because you all have drawn your conclusion. I will just quote, not quote Nick Stern or an ecologist or somebody like that. Quote a poet, dead for a long time, Virgil, the Latin poet. It's in the Aeneid. And it's in book 2 where Aeneas responds to the curiosity of Queen Dido, I don't know, and tells the story of Troy's last days. And the poet writes this: blind with frenzy, we sight the accursed horse on top of our sacred citadel. There Cassandra, who by the gods' decree is never to be believed by Trojans, reveals our future fate by her lips. We, unfortunate ones, for whom that day is our last, clothe the gods' temples with festive branches. Now, nowadays we don't need God Apollo to silence our Cassandras. We do it ourselves. And another poet put it very well. It's T.S. Eliot. There are realities we are unable to face, especially when there is a veil of uncertainty over them. Not completely optimistic, but I can't be optimistic on that matter.